Hey guys, today we're going to take a look at this 12,000 watt inverter by SUNGOLDPOWER. This is by far one of the largest inverters I've had an opportunity to review and test. This thing weighs in at 155 pounds. It came delivered on a pallet from FedEx Freight, and it took two people to lift this thing off the pallet and onto the cart I have it on currently. This is a low frequency inverter, which means it has a massive transformer in here and is why it's so heavy. That big transformer allows it to have a greater output power and start much heavier inductive loads, as well as greater overloading capability compared to a high frequency inverter. This inverter can push up to 15,000 watts for 15 minutes. Additionally, it can push up to 36,000 watts for 20 seconds. That is huge. That is a 3 times overload capability for starting heavier loads. In this video, we'll overview the features, the external connections of the inverter. We'll open it up, take a look inside to see how it's built, the wiring that's used, and the build quality. And then finally, we're going to connect this to my EVE 280 amp hour battery bank that I finally finished building. We'll see if we can push this at or over 12,000 watts and see how it behaves. I am super excited for this inverter for these tests, so let's get right to it. So we got an external temperature sensor. We got a remote. This is just an on-off switch control panel. User's manual. We got a negative and a positive cover for the battery terminals. Yeah, let's see. So taking a look at the front of the inverter first here, we have the on-off switch. The center position is off. Turning it up is power saver mode and turning it down is on. We have a battery type selector. This inverter is a newer model that does support lithium iron phosphate, which is pretty cool. It also supports various versions of lead acid, gel, sealed batteries. There's actually a chart over here which will help you with that. And then various status LEDs to determine the state of the inverter, as well as any fault codes that may have occurred. It's a fairly standard LCD and control panel for these types of inverters. On the right hand side we can see the product information sticker, various ratings of the input-output, as well as the serial number and a few disclaimers and warnings. And we've got two very large fans on the top of the inverter. This inverter pulls air in from the bottom and blows it out the top, or you can also lay it down flat as you see it on the cart currently. That's also an acceptable installation position. Alright, so taking a look at the bottom of the inverter where all the fun stuff is, here we have the main negative and positive input terminals for the 48 volts DC, and they've got some nice serrated flange nuts here for connecting those. We have the remote port where our remote on-off switch will connect into. We have 5 small DIP switches. These will control things such as the frequency. This can do both 50 and 60 Hertz. It will also control battery trip points, power saving configuration, and we have a small dial here on the bottom left for controlling the charge current, and this does contain a 100 amp AC charger, so that's going to be 0 to 100 amps, fairly easy there. We have a small fan which blows air inward. We also have a connection for the battery temperature sensor and a terminal for remote generator start. We have a double pole breaker for the AC input. This is rated for 80 amps. This is a Chint brand breaker. And we have 2 single pole circuit breakers for the AC output. These are 63 amps and are Schneider Electric brand. And these are nice breakers. I'm glad to see Schneider Electric breakers in here. Down at the very bottom here we have a ground connection. We have an AC input, which is leg 1 and leg 2. This does not accept a neutral, so whether you're in the US with split phase or somewhere else, it will only take a leg 1 and a leg 2. AC output, we have a leg 1, leg 2, and a neutral. So if you connect between leg 1 and leg 2, you'll get 240 volts. If you connect between either one of the hots and the neutral, you will get 120 volts. So again, this can operate in any market, whether it be a 240 volt country or a 120 volt country. Additionally, we have a DC output, and I don't see any mention in the user's manual what that is for. And then we have our PV input. This does have a 40 amp MPPT solar charge controller built in. And then we have our grounding block lug on the bottom right. Alright, so now we're ready to open it up and see how it's built. This is always my favorite part of these types of videos. I really like how this enclosure is designed here. So on each side of this inverter, they have these separate panels you can remove and take off without having to remove the cover. Now, of course, you can't really get too much inside. You can see what's in there, but like if you wanted to blow some compressed air or something in here to get the dust out, you don't have to take the entire lid off and disconnect cables. Alright, now there were a few wires under here. which connected the LCD panel on the front, which I've already removed. And you see where they connected there on the front. The first thing we notice in this inverter is the massive transformer that takes up approximately half of this case. And this is really where most of the weight is going to be. It's got this huge iron core. Here's the part number on the side of it. It's made by Liru. I couldn't really find any information on this transformer online. It is Class H transformer, 180 degrees Celsius rating. And this transformer is fed by a pair of very thick conductors. You can see there are 2 for the positive, which go to the first coil, and there are 2 for the negative, which go to the second coil. And these big cables come down, and each one terminates on one of the heat sinks for the transistors. And these transistors you see here are the ones that switch on and off to convert the DC power into AC. There are 16 total transistors on this side of the circuit board. Additionally, we have a temperature sensor here. This inverter is constantly measuring temperature, and it actually controls the fans based on this temperature. So those fans will operate at different speeds depending on a variety of factors, one of which is the temperature of this inverting board. The fans will also operate depending on what percentage load it sees. So in the middle of the heat sinks on the inverter board, we could see several large electrolytic capacitors down in there. I don't want to disassemble this too much, but based on my experience, there are probably 3 or 4 of them in there. Up here we can see the battery comes in, the negative and the positive. The negative goes straight down to the bottom board where the electrolytic capacitors and transistors were. The positive simply comes in and attaches to the side of this heatsink. So looking at the AC portion of this, we have our input AC breaker and our output AC breaker. And all 4 of these connections are a pair of 12 gauge AWM rated wiring. The input breaker goes directly into this top circuit board, and the output leads are going to, well, the opposing side of the same circuit board. So over here we have a set of 4 relays. This inverter does have an internal built-in transfer switch. Following the AC wiring over, we can see the red and the black are the leg 1 and leg 2. Those conductors come off of the transformer, and that's going to be our 240 volts. Additionally, we have a white line here. This is going to be our center tapped neutral. Additionally, we have a very thin 2-conductor wire here, which is just running from the circuit board. It's tie wrapped on here, and it goes over to the fan on the side of the enclosure. The ground screw on the front of the input block is connected to 2 different locations. There's a green wire that comes down here to bond the ground to both the enclosure chassis as well as the giant ground lug on the front. Additionally, we have a thicker 12 gauge wire that comes off of the terminal block and goes up into the main circuit board here. So this entire thing operates on one ground. That includes the chassis, all the components inside, and the grounding terminal on the front. They're all connected. Over here we have our MPPT solar charge controller board. So the solar PV input comes in on both of the center terminals here, and then we have the output positive and the output negative, and both the input and the output are wired with 10 gauge AWM wiring as well. And one interesting note about this MPPT charge controller is this board looks near identical, almost exactly the same but with a few variants, as the circuit board in the PCM60X charge controller. The component placement is all the same, the connection has the same spade terminals up here, the same coil windings at the top, the same transistor placement even. The only difference I noticed really is that these are screws down here for these terminal blocks instead of the big bolts that the PCM60X has. And interestingly, there are even terminals down here that aren't used where the external temperature sensor and battery sense leads will connect. So I think this is actually the same board in the PCM60X, which is kind of interesting. I assume some of these components are readily available on the market, and the manufacturers that build these inverters probably just pull from what's available. So one thing I noticed I think is really cool is both the control board on the top here and the transistor switching board on the bottom. They all have the RU stamp on them, which is the indicator of a UL listed component. So while this unit as a whole is not UL listed, I find it very interesting that these boards are UL listed components, and that's a great sign of quality in my opinion. Everything is insulated with this heat shrink. Every pair of wires, every individual single wire is insulated with heat shrink. The AC outputs are all heat shrinked. They have heat shrink on the gigantic battery leads that come in. All the terminal points are wrapped. You can see anywhere there's a lug crimp, those are all wrapped and heat shrinked as well. All of the little connectors on the boards have this red glue on to prevent them from coming back out. That's wonderful as well. So yeah, all in all, I have nothing at all bad to say about this in terms of build quality. It does look like they went above and beyond some other manufacturers just to ensure quality control, which is great. Out of all this, the only thing I question is the way this fan cable was run under all these conductors that will be heating up without heat shrink protection. But yeah, that's about it. It's time to get it put back together and we'll power it on. So the first thing I want to do before I connect the battery positive and negative and the AC output connection is to make sure these DIP switches are set correctly. Now I'm not going to be testing any of the AC input or MPPT charge controller in this video. This is simply going to be testing the output of the inverter itself as an off-grid standalone system. So the only one of these switches I care about is going to be SW4, and this is regarding the frequency setting. So position 0 is 50 Hz and position 1 is 60 Hz. We are in the United States, so we want this set to 60 Hz, which is position 1, and it is defaulted to position 1, so we're good to go there. Alright, so now we're going to talk about our battery bank. So these are the EVE 280 amp hour batteries, and in my previous video you saw I finally got these new bus bars. They're installed, they're ready to go. The battery bank is assembled here on my test bench for the purposes of testing this inverter, at which point it's then going to be moved outside into my battery shed. You'll notice there's no BMS installed in this battery. Once again, this is a test setup. Anytime you use lithium batteries, you absolutely need to always use a BMS. These batteries were all charged with the BMS, and I know their exact state currently, so I'm just going to be running a discharge test here on the bench, and I'm going to be monitoring it very closely. There were a few questions regarding these bus bars. The biggest question was some of you wanted to see if they can actually handle the rated 300 amps. This inverter is going to pull approximately 12,000 watts through these bars. I have the thermal camera ready, so hopefully get some shots of that. Additionally, some of you guys wanted to see a cutaway of this to see what the layers looked like, so I cut a piece off here. It's nothing too special. You can see it is layered exactly as noted in the listing, and it is pure copper the whole way through with the exception of the first 2 layers. So that's why it's so flexible, because you can see all of those individual layers there. Alright, so these batteries are wired in a 2P16S or 51.2 volts nominal. The main negative is coming off here. It's going through my Batteries shunt so we can watch the amount of current. The main positive is coming off here. It's going down to this 350 amp HRC Class T fuse. Alright, so this battery is going to be pulling a lot of power. So I'm going to be monitoring this very closely at all times. The plan is going to be to run the electric clothes dryer, a 4500 watt space heater, and then 2 smaller heaters off this inverter. And that should push it right around 12,000 watts, maybe hopefully a little bit over, to see what happens. Alright, here's the sub panel I'll be using for this test. I have a 6.3 Romex coming in here. It's very similar to the panel I used before, but I've made a few changes. I have 2 20 amp receptacles here. One is on leg 1 and leg 2 respectively. I have a 30 amp standard clothes dryer outlet. This is slightly different than the one I used before. I've finally upgraded to a 4-prong receptacle and a 4-prong cord on my dryer. And yes, I'm aware this cover plate is on upside down. It is the only one that Home Depot had in stock at the time. I've got a 20 amp 240 volt outlet that we can plug our 4500 watt space heater into. So I typically don't cover AC wiring in videos because you really need to contact an electrician to have this sort of stuff done. There are some dangerous and potentially hazardous voltages in here, and I just don't want to see anybody getting hurt. So please, if you're not sure, contact an electrician. And you can see how I have that connected here. The bare wire is the ground, which is going into the ground terminal. The black goes into hot 1, red goes into hot 2, and the white goes into the neutral. I do not have the AC input connected. Now while I'm on this terminal block, one thing that came to mind, I did discover this DC output is not connected on the other side. These are simply empty. So I imagine this is probably for an additional feature that's not included in this particular inverter. I did notice that when I was putting the enclosure back together, however I forgot to grab a video clip of it. So we have the PV input for the MPPT charge controller, and then once again the DC output is not connected on the other side of this terminal block. Alright, so first the positive goes on, and then we have a safety cover just to protect from any accidental shorts. Alright, so now we're ready to connect the main negative to the battery post on the inverter. This inverter contains some very large capacitors. So when I connect this negative lead, if I simply put it on this terminal, we're going to see a very, very large spark. You know, it always startles people. It makes me nervous as heck to do this step. So before I connect this post, I'm just going to connect this 100 watt 1 ohm resistor between the main battery lead and this post. And this resistor will help limit the amount of current going into the inverter at once. Less inrush means less spark. Now this is only 1 ohms, so there's still going to be a large spark. Ideally this resistor would be larger, but this is what I have to work with. So just got these alligator clips connected to the negative, and that's going into the resistor here. Oh wow, That wasn't what I expected, look at that! So now we can remove our resistor and connect our terminal. And now we're ready to turn it on for the first time. So I'm kind of surprised to hear that fan running because there is no load on it. The charger is not connected, and the heatsink, it's very cold in here, so this fan should be off with all of these conditions met. I'm not sure why that fan is running on this unit with it idling like that. It is pulling 227 watts idle, mostly because of that fan, I'm guessing, because according to the manual this should be around 180 watts of idle. So I don't know what's up with that. Let's just check our panel voltages here. We've got 122 on leg 1, 122 on leg 2, and 245 volts across leg 1 and leg 2, so we're good to go there. Just going to plug in my space heater here. It's 240 volts, I think it's 4,500 watts or 4,000 watts, and turn it on. And you can hear the fans got quite a bit louder, and we're at 4.24 kilowatts. It's looking good. .42 amps or 12.3 kilowatts. That's pretty impressive. So yeah, I think that was pretty good testing there. I did leave it run for about 15 minutes at the 12 kilowatt load, and then I had shut off the space heaters and the bulbs and just ran the clothes dryer for the rest of the time. All in all, I pulled approximately 7 kilowatt hours from the battery by the time the dryer had shut off. So I do feel that was a pretty good test of the inverter. And as you can see, it had no problems whatsoever handling that heavy load. So the only thing that I really question is why that fan is running constantly in there. It should be idling around 185 watts without that fan running. So taking a look at some of the thermal pictures here, most of the heating occurred on the cabling at or where the terminal lugs were crimped on. So here you can see we have 40 degrees Celsius at the shunt crimp connection, and the hottest crimp at the inverter was 25 degrees Celsius. And here's where the negative connected to the battery post was at 46 degrees Celsius. There was no thermal problems at all in the terminal block of the inverter. That maxed out around 22 degrees Celsius. And here you can see one of the bus bars that was a parallel connection at 24 degrees Celsius. And then I also checked all the series connections as well. So here's a series connection at 22 degrees Celsius. This connection would have had the full 225, whatever it was, amps flowing through it. So as you can see, these bus bars are more than capable of handling a good amount of power. And the hottest part of the inverter was the top cover, which checked in at 26 degrees Celsius. Other things I noticed included that the output voltage was around 242 volts. My larger Ames inverter puts out 230 volts. 240 is the NEC standard. But other than that, the only downside of this inverter is the idle consumption, just like the last one we tested. A few people did mention in the past about the power saving mode, and I did do a video in the past showing why I don't find the power saving mode to be particularly useful. And the way that works is it just pulses power through on one of the two legs until it finds a load and turns the inverter on. So yes, you could use the power saving mode, but as I've explained before, I don't find that useful for myself. I will leave a link in the description to where you can find more information on this inverter. The manufacturer did want me to let you know that there is a sale going on through December 5th, and that sale will take $300 off either their 12 kilowatt, 15 kilowatt, or 18 kilowatt model inverters. So if you're interested in that, again, there'll be a link down in the description of this video. I would love to test the transfer switch, the AC input, and the charger of this inverter at some point. Maybe I can do that by wiring it up to a second inverter and see how it behaves like that. But if I decide to do that, it will be done in future videos. If you like what you saw here, please hit that like button before you go. As always, feel free to leave questions or comments down below. I always read and reply to as many of those as I can. Otherwise, thanks for watching.